Section 4 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Some Valuable Electrical Processes. Students of that branch of science known as physics are coming to the conclusion that electricity plays a much more important part in the universe than was supposed. They are led to believe that electrical attraction is the cement which binds together those exceedingly minute particles out of which everything is built up. Whether electricity binds them together or not, it is certain that electrical action can in some cases separate those particles, and this process of separation provides a means of carrying on some very remarkable and useful industrial processes. Let us imagine a vessel filled with water to which has been added a little sulfuric acid, while suspended in it are two strips of platinum. There is a space between the strips, so that when their upper ends are suitably connected to a source of electric current, that current flows from one strip to the other through the liquid. That is an example of the apparatus for carrying out this electrical separation in its simplest form, and it will facilitate the further description if the names of the various parts are enumerated. The process itself is electrolysis. The liquid is the electrolyte, while the strips are the electrodes. The individual electrodes, again, have special names, that by which the current enters being the anode, and that by which it leaves the cathode. It is not difficult to remember which is which if we bear in mind that the current traverses them in alphabetical order. Since, however, it may not be easy for the general reader to carry all these terms in his mind, we will, when it is necessary to differentiate between the two electrodes, call one the in electrode and the other the out electrode. Returning now to our imaginary apparatus, let us turn on the current. At first, nothing seems to be happening, although suitable instruments would show that current was flowing. Soon, however, little bubbles appear upon the electrodes, and these grow larger and larger until they detach themselves from the platinum to which they have been adhering, float up to the surface, and burst. The question which naturally arises is, what do these bubbles consist of? Are they air? If we take means to collect the gases which formed them, we get an unmistakable answer. The bubbles which arise from the in electrode are oxygen, those from the other, hydrogen. If we allow our apparatus to work for some time and collect all the gas which arises, we shall find that there is twice as much hydrogen as oxygen. We shall also find, as the process goes on, that the quantity of water diminishes. Perhaps I may be allowed at this point to remind my readers that water is a collection of minute, ultramicroscopic particles called molecules, each of which is formed of three smaller particles still, called atoms. Of the three atoms, two are hydrogen and one oxygen. Water, therefore, consists of hydrogen and oxygen, there being twice as much of the former as there is of the latter. We see, therefore, that electrolysis gives us hydrogen and oxygen in exactly those proportions in which they occur in water, and since we also see that as these gases appear the water itself disappears, we are led to conclude that the current is splitting up the water into the gases of which it is formed. But the strange thing is that this will not work with pure water. We have to add something to it. In the case of our imaginary experiment, it was sulfuric acid. What part does that play? This is not fully understood, but we may be able to form a mental picture of what is believed to happen as follows. The in electrode is surrounded by a vast assemblage of these tiny molecules, most of those of water, but a few of those of acid. The latter are more complex in their structure than the former, but they too contain hydrogen. Current flows into the electrode and instantly hydrogen atoms from the acid molecules crowd round it, like boatmen at the seaside anxious to secure a passenger. Each takes on board a quantity of electricity and with it darts across the intervening space to the other electrode. Arrived there, it gives up its load and, its work done, remains lying upon the electrode until enough others like unto itself have gathered there to form a bubble and so escape. These hydrogen atoms are thought to be the craft which carry the current through the liquid and enable it to pose, as it were, as a conductor of electricity, which in reality it is not. But where does the oxygen come from? To find the answer to that, we must add a second chapter to our story. When the hydrogen boats took on board their load of electricity, they left their former associates, and these forthwith set upon neighboring water molecules, and with the audacity of highwaymen stole from them enough hydrogen atoms to take the place of those they had lost. Thus the acid molecules became complete once more, while the scene of the conflict near the in-electrode was strewn with the remains of the water molecules from which the hydrogen atoms had been stolen. These remains, of course, would be oxygen, and they, collecting together on the electrode, would eventually be in numbers sufficient to form bubbles and so escape. Thus it may be the acid which really does the work, yet because of its subsequent raid upon the water, it is the latter which disappears, and it is the materials of the latter which are brought to the surface in the bubbles. And there we see the mechanism whereby, so it is believed, electric current can pass through otherwise non-conducting liquids. And the important part, as far as practical utility is concerned, is that the passage of the current is accompanied by a splitting up of something or other, either the water or something in it, the materials of which are deposited, one on one electrode and the other on the other. And now we can proceed to those useful applications of electrolysis, the commonest of which, perhaps, is electroplating. We have seen how electrolysis causes hydrogen, probably out of the acid, to be deposited upon one electrode. Suppose that, instead of an acid, we put in the water one of those substances known to chemists as a salt, the commonest example of which is ordinary table salt. This well-known condiment is caused by the interaction of hydrochloric acid and the metal sodium, and will serve to illustrate what all salts are. All acids are compounds of hydrogen and something else, and their biting action is due to the readiness which the something else evicts the hydrogen and takes in a metal in its place. Thus, hydrochloric acid, given the opportunity, gets rid of its hydrogen and takes in sodium, thereby forming chloride of soda or a common salt. Another example is the gold chloride familiar to photographers. This is the result of the action of certain acids upon gold, wherein the acids throw out their hydrogen and take in gold instead. To sum up, then, a salt is just the same sort of thing as an acid, like the sulfuric acid which we used in our experiment, except that some metal has taken the place of the hydrogen. It is not surprising, then, to find that if we put a salt in the electrolyte instead of an acid, we get a similar result. In one case, hydrogen is deposited upon the out electrode, in the other, the metal. In the former case, since hydrogen is a gas, it forms bubbles and floats away, but in the latter the solid metal remains a thin, even coating upon the electrode. This is the principle of electroplating. The electrolyte consists of a suitable solution containing a salt of the metal to be deposited, and it is placed in an insulating vessel or vat. The articles to be plated form the out electrode, so that they have to be suspended in some convenient way from a metal conductor by conducting wires. Of course, they are entirely immersed in the liquid. The in electrode is sometimes a plate of platinum, the reason for that expensive metal being used being that it is unaffected by the chemicals, or else a plate of the metal being deposited. In the former case, the solution becomes weaker as the work proceeds, and more salt has to be added. In the latter, however, the strength of the solution remains unchanged, for by an interesting interchange the in electrode adds to it just what it loses by deposition upon the other one. The effect is therefore just as if the current tore off particles from the one and placed them upon the other. This is believed to be due to the agency of the oxygen, which in the case of the electrolysis of water becomes free, but which in this case forms with the metal electrode a layer of oxide upon its surface, this oxide being then dissolved away by the liquid. Thus, as fast as the metal is deposited upon the out electrode, its place is taken by more metal from the in electrode. In some processes, it is desired to deposit metal upon a non-conducting surface, and it is evident that such cannot be used as an electrode. Nor is it any use to attempt to deposit upon anything except an electrode. The only thing to do, then, is to make the object a conductor by some other means. Models in clay, wax, and plaster, once living objects like small animals, fruit, flowers, or insects, can, however, have a perfect replica made of them by electrical deposition, by the simple method of coating the surface to be plated with a thin layer of plumbago. This skin, although extremely thin, is a sufficiently good conductor to make the process possible. Process blocks for printing are copied in this way, so that a particularly delicate example of the blockmaker's art need not be worn down by much pressing, copies or electros being made off it for actual use in the press. The original block is a plate of copper on which the picture is represented by minute depressions and prominences. On this a layer of soft wax is pressed, so as to obtain a perfect but reversed copy. Having been coated with plumbago, this is then put into a vat containing a solution of copper salts and is used as the out electrode, the other being a plate of copper. When the current is turned on, the copper is thus deposited on the wax until a thin sheet of copper is formed which is an exact but reversed copy of the wax, a direct copy, that is, of the original block. The back of this thin sheet is then covered with molten lead or type metal to fill up any depressions and to give it sufficient strength. Anyone who has seen one of these half-face blocks covered with minute depressions so slight they can scarcely be seen, yet so perfect that a beautiful print can be obtained from them, will realize the wonderful power of this electrolytic process, and the marvelous accuracy with which the original is copied, and the unerring way in which the electrical current carries the particles of copper into every one of the myriad recesses in the wax. Another specimen of the marvelous work of this system is the wax cylinder of the phonograph. The sound is produced by a needle traveling along a groove of varying depth cut in the surface of the cylinder. This groove forms a spiral, passing round and round like the thread of a screw, and it encircles the cylinder 100 times in every inch of its length. Consequently, at any point one may take, there is but 1/100th of an inch from the center of one turn to the center of the turn on either side of it, and at its deepest the groove is less than 1/1000th of an inch deep. The phonograph itself cuts the first master record, as it is termed, and the problem is to take a number of casts off this model of such delicacy and accuracy that every variation in that exceedingly fine groove shall be faithfully reproduced. Such a task might well be given up as hopeless, but with the help of electrolysis it is accomplished easily and cheaply. To attempt to press anything upon the surface of the master would but smooth out the soft wax and obliterate the groove altogether. To apply anything softened by heating would be to melt it. But electrolysis, without tending in any way to distort or damage the delicately cut surface, deposits upon it a surface of metal from which thousands of casts can be made. The gentle fingers of the electricity overlay the soft wax with the hard, strong metal with a minute perfection almost beyond belief. To commence with, the master record is placed upon a sort of turntable in a vacuum, and turned round in the neighborhood of 2 strips of gold leaf strongly electrified. By this means the gold is vaporized, and a perfect coating of gold is laid upon the wax. This is far too thin to be of any use except to render the cylinder a conductor, for the coating is so fragile that it is no stronger than the wax itself. It enables the cylinder, however, to be electroplated with copper until it is surrounded by a strong metallic shell 1/16th of an inch thick. It takes about 4 days to deposit this thickness. The copper shell is then turned smooth in a lathe and fitted tightly into a brass jacket. A little cooling causes the wax record to shrink sufficiently to free it from the copper shell and allow it to be lifted out. A copper mold is thus formed in which any number of additional records can be cast. The molten wax is simply introduced into the inside and allowed to set. The inside is bored out in a lathe, and then with a little cooling it shrinks and can be withdrawn. A completely finished record, every tiny depression or swelling in the original master being reproduced with an accuracy almost incredible. Another valuable use to which this process is put is the purification of metals. The electrochemical action works with unerring precision. It never mistakes an atom of iron for an atom of copper, for example. Passing through a solution of copper salt, the current deposits only copper. For modern electrical machinery and apparatus, copper is required of the utmost possible purity, for every impurity adds to its electrical resistance, in other words, diminishes its value as a conductor. Consequently, thousands of tons of electrolytic copper, as it is termed, are produced every year. The electrodes used are plates of ordinary copper. A coating of pure metal is deposited by electrolysis upon the out electrode from the other one. When the deposit is thick enough, the out electrode is taken out and the deposit torn off it, the union between the two being sufficiently imperfect for this to be done without difficulty. The metal of which the in electrode is made has already been purified by other processes, until it contains but 1% of foreign matter, and by this means even that small percentage is entirely got rid of. The impurities fall to the bottom of the vessel in the form of slime, which is periodically removed. And not only is electrolysis thus unerring in picking out certain atoms from among a mixture, but there is an exact relation between the work being done and the quantity of current used. Consequently, it forms a very exact method of measuring currents. The method of measuring current by the strength of the magnetic field which it produces has been mentioned already, and such measurements can be checked by electrolysis. Thus, the practical definition of the ampere is that current which when passed through a solution of silver nitrate in water will deposit silver at the rate of 0.001118 gram per second. The electric accumulator, or secondary battery, one of the most useful appliances, is the result of electrolysis reversed. Many large electric lighting plants have, in addition to their generating machinery, a large battery of secondary cells which, being kept charged, are able to help the machinery in times of heavy demand, or even to supply the whole current needed for, say, half an hour, so that the whole of machinery could, in the event of an accident, be shut down for that time and the supply maintained from the batteries. This would be sufficient, in many cases, for fresh machinery to be brought into action or emergency arrangements to be made. It may be that this book is being read by someone seated serenely in his armchair, while engineers and workmen at the generating station are working in frantic haste to set right some sudden breakdown before the batteries are run down. The batteries may have saved the town half an hour's darkness. Large telegraph offices are fitted with secondary batteries. Many motorists owe the ignition which keeps their engines at work to secondary batteries. It is secondary batteries which keep the wireless apparatus at work on a wrecked vessel after the engines have stopped. Indeed, secondary batteries are one of the most beneficent inventions, and if only they could be made in a lighter form than is possible at present, their value would be infinitely increased. We have seen how the passage of current through acidulated water produces hydrogen and oxygen. If those gases be collected in closed vessels over the water, so that they remain in contact with the water, as soon as the current is stopped, a reverse action sets in. The gases tend to recombine with the electrolyte, and in doing so give back a current equal to that which formed them. Figure 4 shows the construction of what is called a voltometer, in which the gases arising from the electrodes are collected in little gas phials placed just above them. Such an apparatus enables us to see easily how the accumulator works. The picture shows the battery which is effecting the separation of oxygen and hydrogen. If that be disconnected and the wires joined, as shown by the dotted line, a current will flow back until the oxygen and hydrogen have returned into the solution again. The apparatus will, in fact, work like an ordinary battery, except that instead of a plate or rod of zinc, a mass of hydrogen will form the essential part. An appliance such as a voltometer is not of much use for the practical purpose of storing large quantities of electrical energy because the surfaces of the electrodes are so small, and the surfaces where the liquid and gases are in contact are small too. It is clear that the larger the electrodes are, the wider will be the passage for the current, just as a wide road can accommodate more traffic than a narrow path. We may regard the electrodes as like gateways through which the current passes. By making them large, therefore, we enable a large current to pass, and consequently permit electrolysis to take place with greater comparative rapidity. The plates, as the electrodes in a secondary battery are termed, are generally large metal plates. Experiment has shown that lead is the best for this purpose. It has also been found that it can be improved by making it porous, since the inner surfaces of the pores are so much added surface through which current can pass into the electrolyte. There are various ways of producing this porosity, which need not trouble us here, however. It will suffice for our purpose to understand that an ordinary secondary cell consists of two lead plates, with the largest possible surface, immersed in a liquid, generally a dilute solution of sulfuric acid in water. To charge the battery, current is sent to one plate, through the liquid to the other plate, and so away. A thin film of hydrogen is thus formed upon the outgoing plate, while oxygen is formed at the incoming one. Since the hydrogen is spread over such a large area, it does not accumulate sufficiently for it to rise to the surface. Most of it remains adhering to the plate. The oxygen combines with the lead of its plate, and so is safely stored up there in the form of oxide of lead. This storage of hydrogen upon the one plate and oxygen on the other cannot go on indefinitely, and so as soon as the limit is reached, the cell is fully charged. Passage of further current is then simply a waste. The dynamo or primary batteries which are used for charging having been disconnected, the two plates can be connected together through lamps, motors, or in any other desired way, and the current will flow out again, the opposite way to that in which it entered, just as a stone thrown up in the air returns the opposite way. The current which comes out is, in fact, a sort of reflex action arising from that which went in, the mechanism by which is produced being the reabsorption of the oxygen and hydrogen into the electrolyte. Whether a cell is fully charged or not is ascertained by weighing the electrolyte, an operation which at first sight seems to have nothing whatever to do with the matter. It arises from the difference in weight between water and sulfuric acid, the latter being the heavier. We have seen that while a little acid must be added to the water before it can be electrolyzed, it is the water which is ultimately resolved into its constituent gases. Hence, the result of electrolysis is to increase not the amount, but the proportion of acid. Therefore, it increases the weight of the electrolyte. This weight is ascertained by means of a hydrometer, a glass tube stopped and loaded with some small shot at its lower end. On the upper part is engraved a graduated scale, so that the exact depth to which it sinks can be easily read. This depth will, of course, vary with the specific gravity of the liquid, and so the depth recorded by the scale will be an indication of the proportion of acid, and that in turn will show how far the process of charging has progressed. Accumulators are, or have been hitherto at any rate, very troublesome things. They are apt to lose their power. If not properly charged, they are easily damaged. Too rapid charging, or too rapid discharging, standing for a while only partially charged, all these things have a bad effect, in extreme cases even destroying them altogether. Because of the use of lead, they are terribly heavy too, so much so that for traction purposes they are of very little use, for a large amount of the energy stored in the accumulators is then used up in hauling them about. Yet what a field there is for the successful accumulator! Take the one instance of the electrification of a railway. If good light and efficient accumulators were to be had, no alteration at all would be necessary to the permanent way. The engines or motor carriages would need to go periodically to a depot to be recharged, but that could be easily arranged. Such things as conductor rails, overhead conductors, and so on would be needless. The world has therefore been interested for years in the rumor that T.A. Edison was engaged upon this problem, and at last he has produced his accumulator, by which he has removed many of the difficulties, if not all. Instead of a case of glass or celluloid, as is usual with the older cells, his cells are enclosed in strong boxes of nickel steel. The positive plate consists of nickel tubes filled with alternate layers of nickel hydroxide, while the negative plate is formed of prepared oxide of iron in a nickel framework. The electrolyte is a solution of potassium hydroxide. The chemical action and the electrical reaction is, of course, on the same principle precisely as in the older cells, but it is claimed that the Edison cells are foolproof. That is to say, they cannot be damaged by careless handling, and they appear to be a little lighter. Thus the problem is partly solved, and with that as a fresh starting point, someone may sooner or later give us a secondary battery which is light as well as strong. If any would-be scientific inventor reads these words, there is a suggestion for a promising line of investigation. End of section 4. Section 5 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Machine-made cold. One of the most remarkable adaptations of scientific knowledge is the manufacture of cold. At first, that phrase seems strange, but it is really quite legitimate. There are machines at work at this moment which are turning out cold as if it were any other manufactured article. It is not that they manufacture cold water or cold air, it is the cold itself which they produce. Of course, cold has no real existence, since it is simply a negative quantity, an absence of heat, yet its effects are so real that we are in the habit of talking of it as if it were a reality, and in that sense we can regard it as a product of manufacture. Moreover, we see in this a conspicuous instance of the interdependence of invention and science, for scientific principles were first adapted to produce cold, and then artificial cold was employed in scientific inventions, whereby the rare gases of the atmosphere have been discovered, as we shall see presently. In mechanical inventions of today, I have dealt with the uses which can be made of heat as a motive power. Here we have in some sense a reversal of the process. In the heat engine, the expenditure of heat produces motion. In the refrigerating machine, motion produces heat. On the face of it, a strange way of producing cold. Yet it is by the production of heat in the first instance that we are ultimately able to obtain the cold. One way to make a thing cold is to place it in contact with ice, but that process suffers from severe limitations. In the first place, we may not be able to produce ice when we want it, and in the second place, we may want to produce a temperature much lower than that of ice. Now a machine can produce any degree of coldness, almost down to the absolute zero, the point at which a body is absolutely devoid of any heat whatever, the condition in which its molecules are absolutely still. That point is 274 degrees Celsius below freezing point. Freezing point on that scale is zero, and so this absolute zero is minus 274 degrees. Or, to put it another way, freezing point is 274 degrees absolute temperature. The absolute zero has never been reached, and there is reason to believe that it never can be quite reached, but by methods about to be described a temperature within a few degrees of it has been attained, and all of this can be done without any cooling agent colder than water at an ordinary temperature. There are several systems, but the one which illustrates the principle most simply is that in which carbonic acid gas is the working fluid. This is a very compressible gas, and so is well fitted for the purpose. First of all, a pump or compressor compresses it. That has the effect of heating it. Such we might expect from the fact that heat is molecular activity. When by compressing the gas we force the molecules closer to each other, they naturally hit each other and the sides of the container vessel harder than they did before, and the increased activity is manifested as increased heat. So the first effect, as was remarked just now, is to produce, apparently, increased heat. But then the hot compressed gas, by being passed through a coil of pipes surrounded by cold water, can be robbed of that heat. According to the speed at which it traverses the coil, it will be more or less cooled. By causing it to travel slowly, it can be brought down almost to the temperature of the water. So we start with the gas at atmospheric pressure and at somewhere about atmospheric temperature too. This we convert into compressed gas at high temperature. After cooling it, we have compressed gas at a moderate temperature. Then, to complete the process, we let the gas expand again. Now, just as compressing a gas heats it, letting it expand cools it. If we compressed it and then expanded it again, we should be just as we were to commence with. But since, in between the two operations, we extracted a quantity of heat by means of the cooling water, we get at the very end a much lower temperature than that with which we started. We cannot cool the gas without compressing it, because heat will only flow from one body into another when the second is cooler than the first. But, by making the gas hot temporarily by compression, we enable the water to draw some heat from it, and then, allowing it to sink back to its original state, we get practically the old temperature, less what the water has extracted. The principle is really absurdly simple when one once gets to understand it. The application is not so simple as far as the designer of the machine is concerned, for he has to adjust the various parts to exactly the right shape and dimensions, so that they may work well with one another and produce the desired result with the minimum expenditure of power. To the observer, however, and to the user too, The finished machine is wonderful in its simplicity. The principle is illustrated diagrammatically in Figure 5. In the center is the compressor. Its action forces the gas along the pipe to the right and down into the condenser. As it flows downward through the coil, there cold water enters at the bottom of the tank, flows upward past the coil, and escapes again at the top. Thus the coil is kept in contact with cold water. Passing then through the bottom of the tank, the gas travels from right to left through the regulating valve and into an arrangement almost exactly similar to the condenser, but called the evaporator. Here the gas expands and suffers a great fall in temperature. This cold is communicated to liquid circulating in the tank, which forms part of the evaporator, and this liquid can be circulated through pipes into any rooms to be cooled, or around vessels of water which it is desired to freeze. This liquid, which acts as the carrier of the cold, is called brine, and is water to which is added calcium chloride to keep it from freezing. Now the observant reader may have noticed that there is no apparent reason for the name of the left-hand vessel. It will be quite clear, however, when I explain that although I have spoken of the working fluid all along as a gas, I have only done so to avoid bringing in too many explanations at once. It is actually liquid for a good part of its journey. Carbonic acid gas liquefies at a very moderate temperature and pressure, and so, while it leaves the compressor as a gas, it becomes liquid in the condenser and remains so until it has passed the regulating valve. Then it begins to expand into gas once more, and in that state it passes back to the compressor. There is a pressure gauge on the pipe leaving the compressor and another on the one entering it. A comparison of the readings of these two tells how the apparatus is working. The difference between them indicates how much compression is being given to the gas. Assuming that the compressor is working at a constant speed, this compression can be regulated to a nicety by the valve. Close it a little and the compression will increase. Open it a little and the compression will decrease. By this means the degree of cold produced can be varied at will. This is the way in which many ships are enabled to carry cargoes of frozen meat. The chambers in which the meat is stowed are insulated, that is to say, their walls are made as impervious as possible to heat. Then the brine is carried into the chamber in pipes, cooling them much as the hot water pipes heat an ordinary public building. Or another method is to carry the pipe which constitutes the evaporator into the chamber to be cooled. A third way is to dispense with the brine and to blow air through the coils of the evaporator, whereby the air is made to carry away the cold to wherever it is needed. Ice can be made easily in molds of metal or wood around which brine circulates. If made of ordinary water, the ice is likely to be cloudy and opaque, which is quite good enough for many purposes. In cases where it is desired that it should be clear, the water is agitated during freezing, or else distilled water is used. To enable the blocks to be got out of the molds, it is sometimes arranged to circulate warm brine for a few moments. Ice skating rinks are formed by making first an insulating layer of sawdust, slag wool, or something of the sort, those, by the way, being the materials generally used for insulating cold chambers, underneath the floor. The floor, too, is made waterproof, and then upon it is laid as closely as possible a series of iron pipes. Water is flooded onto the floor until the pipes are covered to a depth of several inches, and then brine is pumped through the pipes. In time the water freezes, and so long as the brine circulates, it remains so. But although the CO2 process, described above, is the simplest illustration of the principle, there are other systems. In one very popular form, ammonia gas is the working fluid. This is liquefied by pressure and cooling with water, being subsequently expanded just as described above. Another much-used system is the ammonia absorption process, in which the ammonia is not liquefied, but when under pressure is absorbed by water, returning to gas again when the pressure is released. But the degree of cold attained in these commercial machines is as nothing to the extremely intense cold generated on the same principles in the liquid air machine, which is found in every well-equipped physical laboratory. Briefly, this consists of a coil of many turns of small tube enclosed in a small double vessel, the space between the inner and outer skins of which is packed with insulating material. A compressor pumps air in the top of the coil at a pressure from 150 to 200 atmospheres. An atmosphere, it may be remarked, is a unit often used in scientific matters, meaning the normal pressure of the atmosphere, which is, roughly speaking, 15 pounds per square inch. Hence, 200 atmospheres is about 3,000 pounds per square inch. Of course, air so highly compressed as that is hot, but after it has passed down the coil and has escaped from the valve which liberates it at the bottom, it is much cooler. But that is only the beginning of the operation. The expanded, and therefore cooled, air finds its way upward through the turns of the coil down which the following air is coming. That, expanding in its turn, is colder still, because of the cooling action of the first air, and so the process goes on. This is perhaps easier to understand if we imagine that the air comes through the coil in gusts, and we notice what happens to each succeeding gust. The first comes down, expands, cools, and ascends, thereby cooling the second gust as it comes down. The second, then, after expansion, will be cooler than the first was. That, in its turn, will cool the third, and so the third after expansion will be cooler than the second. And that will go on, each succeeding gust being cooler than the one before, and although the flow of air is continuous, and not in gusts, the result is just the same. It goes on getting cooler and cooler until at last the air comes out in its liquid form. This liquid collects in a little chamber formed at the bottom of the vessel which contains the coil, and can be drawn off when desired. Air in its liquid state looks very much like water. In fact, it is difficult to get chance observers to believe that it is not water. It boils at a temperature far below the freezing point of water, so that liquid air, if placed in a cup made of ice, will boil furiously. Ice is so much the hotter that it behaves towards liquid air as a very hot fire does to water. The feature of the above machine, it will be noticed, is that no cooling water is required, as in the refrigerating machine, although the principle of the two is the same. The coil is the condenser, and the vessel in which it is enclosed is the evaporator, and so the cold air produced by the process in the evaporator cools the coil of the condenser. Thus it is self-intensive, as the makers call it. Hydrogen can be liquefied in a similar machine, except that it needs a little preliminary cooling with liquid air. Liquid hydrogen is the coolest thing known, approaching the region of absolute zero. And now we can turn to the wonderful discoveries which have followed upon the manufacture of liquid air. To make the story complete, we need to go back to the time of Priestley and Cavendish, early in the last century. They investigated the atmosphere and showed that it consisted of oxygen and nitrogen in certain invariable proportions, with, under certain conditions, a small portion of carbonic acid. These facts were so well authenticated, and they seemed to explain everything so satisfactorily, that it was quite thought almost up to the end of the 19th century that there was nothing more to learn about the atmosphere. Nevertheless, there was an idea in the minds of some scientists that there must be another group of elements somewhere, the existence of which was then undiscovered, but it was never dreamed that these were in the air. Soon after the weights of the atoms had been found, a medical student named Prout, in an anonymous essay, called attention to the fact that there were curious numerical relationships between them. Speculation on the subject went on for many years, until in 1865 the great Russian chemist Mendeleev published his conclusions. He had arranged the elements in the form of a table in the order of their atomic weights. The table consisted of 12 rows of names forming 8 vertical columns, and the remarkable thing was that all those elements which fell into any particular column, although their atomic weights were very widely different, had similar properties. This enabled him to predict the discovery of certain new elements, for the table contained a number of blank spaces. 3 elements have been found since, and their atomic weights and properties are just such as to fill 3 of the blank spaces. One blank space, it is thought, may be filled some day by the gas coronium, which like helium has been discovered in the sun, but unlike it has not yet been detected here. When it is, there is the place in the table which it may fill. The table then commenced with what is called Group 1, but for reasons too complicated to explain here, it appeared as if there must be a group before that, a group the chief characteristic of which would be the inactivity of the elements included in it. These were expected to be of various atomic weights, but these weights, it was anticipated, would so occur in the intervals between the others so that they would all fall into a new column to the left of Group 1. In the year 1892, Lord Rayleigh was investigating the question of the density of a number of different gases, including, so it happened, nitrogen. Now there are several ways of procuring nitrogen. One is to get it from the atmosphere by ridding it of the oxygen with which it is normally mixed. Another way is to split up some compound, such as ammonia, of which it forms a part, in such way as to catch the nitrogen and leave the other elements with which it was combined elsewhere. Lord Rayleigh tried both ways, and he found that the nitrogen from the atmosphere was denser than that derived from ammonia. Sir William Ramsay then carried the matter a step further. He heated atmospheric nitrogen in the presence of magnesium, under which conditions some of the nitrogen combines with the latter element to form nitride of magnesium. That, it was found, made the remaining nitrogen denser still. The explanation seemed obvious. Suppose we imagine a mixture of sawdust and iron filings. It will be heavier than an equal quantity of pure sawdust. And if we contrive to take away some of the sawdust from the mixture, we shall find that what is left is heavier still when compared with an equal bulk of pure sawdust. For it is clear that as we take away sawdust, we thereby increase the proportion of the heavier iron filings, and so we make the mixture heavier. Applying a similar process of reasoning to these discoveries, the conviction grew that the nitrogen of the air was not pure, but that it had mixed with a small proportion of some other gas of greater density. They soon succeeded in isolating this denser gas, to which they gave the name of argon. Its atomic weight was found, and, wonderful to relate, it was such that argon fell into a new column to the left of Group 1, as had been anticipated. The discovery of argon was announced in 1894. The next year, Sir William Ramsay, investigating a gas which had been discovered locked up in the interstices of a mineral called cleveite, was able to state that it was helium, the element which had been previously noticed by the spectroscope in the sun. Like argon, it was found to be extremely inactive, and its atomic weight turned out to be such that it, too, fell into the zero group. In 1898, Professors Ramsay and Trevor found two more gases in the air, krypton and neon, and a little later still there was found mixed with the krypton a further new gas, xenon. All of these had their atomic weights found and fell into that new column in the periodic table. But what has all this got to do with liquid air? The two subjects are closely related, for it is by liquid air machines that these rare gases are now obtained, and it was from liquid air that the last three were first discovered. For air, as we well know, is a mixture of gases, and when extreme cold and pressure are applied, these gases liquefy, each behaving according to its own nature. They do not all liquefy at the same time, nor, on being relieved from pressure and heated, do all evaporate again at the same temperature. Although they emerge from the liquid air machine in the form of a single liquid, it is really a mixture of liquids, each with its own boiling point. In an earlier chapter, we saw how petroleum can be separated into its various constituents, such as petrol, by fractional distillation, advantage being taken of the difference in the boiling point of the various fractions. The boiling point of a liquid is, of course, the temperature at which it turns freely into vapor, and just as petroleum, when heated, first gives off cymogene, next rhylogene, then petrol, benzene, kerosene, and so on in the order named, so liquid air, when it is evaporate, gives off its different constituents in order. Nitrogen, oxygen, argon, helium, krypton, neon, and xenon can all be separated each from the others in this way, by fractional distillation. The heat from the surrounding objects is allowed to get at the liquid, and the gases are then given off in the order of their boiling points. And thus we see how the mechanical production of cold has assisted in the pursuit of pure science. The newly found gases are not of any great use at present. They are so inactive that possibly they never will be, with one exception, and that is neon. If an electric discharge be made to pass through a tube filled with this gas, a beautiful glow is the result, and it is just possible that neon tubes may become the electric light of the future. That is only a prediction, however, and a hesitating one at that. The inactive elements may become of value in explosives. We have seen how important nitrogen is in these dangerous substances, the chief feature of which is their instability. their readiness, that is, to change into something else, which instability is due to the reluctance with which nitrogen enters into them. Now nitrogen, though inactive, is much less so than these others, and if a way should ever be found of inducing them to enter into a compound, that compound will probably be an extremely powerful explosive. End of section 5.
Section 6 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Arvind Sundar from arvindsundar.com. Marvels of Scientific Invention by Thomas W. Corbin. Scientific Inventions at Sea. The safety of our fellow creatures has always been a strong stimulus to our inventive faculties. The occurrence of a bad railway accident, and roughly its nature, can be inferred from the files of the Patent Office, for such an event brings men's thoughts to devising ways and means of preventing a recurrence, and an avalanche of such inventions descends upon the Patent Department in consequence. In like manner, a particularly distressing accident to a lifeboat some years ago brought out many inventions for the improvement of those romantic craft. Many of the inventions which arise under these conditions are, of course, utterly worthless, but some of them come to stay. It is not surprising, therefore, when we think of the almost innumerable wrecks which happen, even with modern shipping, that human ingenuity has been extremely busy in devising ways for bringing more of safety and less of risk into the lives of those who go down to the sea in ships. Of these, perhaps none is more fascinating than the modern lighthouse, with its tall tower, its brightly flashing light, standing undisturbed in the wildest storm, quietly and persistently sending forth its guiding rays, no matter how the elements may be buffeting it. There is something specially attractive in this perfect embodiment of quiet strength and devotion to duty. Of course, its origin is very ancient. One of the earliest inventions, no doubt, was the bright thought of a very primitive man who lit a fire on a hill to serve as a guide to some belated friends out in their fishing canoes. From some such beginning, the modern lighthouse, a magnificent product of the science of civil engineering and the science of optics, has arisen. Of the difficulties encountered in the construction of lighthouse towers on outlying rocks, much has been written. The historic Eddystone, for example, has quite a voluminous literature of its own. Of the light itself, however, much less is known. It will be interesting first to note the different purposes for which a light may be required, and then see how the apparatus of the lighthouse is made to serve these purposes. There is the making light, perched, if possible, upon some high eminence, deriving its name from the fact that the sailor sights it as he is making the land. Vessels approaching England from the southwest by night first see the light at the Lizard. The transatlantic vessels know they are approaching land by catching sight of the Fastnet Rock light off the coast of Ireland. Cape Race light serves in the same way for those about to enter the St. Lawrence, and Navesink for the entrance to New York Harbor. All such as these have to be of the greatest power practicable, so that they may be visible not only at the longest possible distance, but also under unfavorable conditions, such as haze and slight fog. No light, of course, can penetrate thick fog, but in light fog and haze a powerful light can be seen at considerable distances. For the same reason, these lights must be high up, or the curvature of the ocean surface will limit their range. A light elevated 100 feet above the sea level will be visible nearly 16 miles away, but if only 50 feet up, it will be invisible at 13 miles. To be seen 40 miles away, it must be as high as 1,000 feet. But then again, height is in some cases a disadvantage, for sometimes fog hovers a little distance above the sea, while below it the air is clear, and the higher a light may be, the more likely is it to have its lantern immersed in a floating cloud of fog. Many readers familiar with the south coast of Britain will remember that the light which used to show on the summit of Beachy Head is there no more, but has been replaced by a tower at the foot of the cliffs, the reason being that it may be below the clouds of fog which are prevalent at that point. But the mention of Beachy Head introduces us to another class of lights, known as coasting lights, since they are intended to lead the mariner on from point to point along a coast. It will be seen at once that in many cases they do not need to be visible at such great distances as the making lights. When the mariner has sighted the lizard, for example, he knows where he is. In order that he may learn that important fact as soon as possible, it is desirable that the light should have the greatest possible range. But having thus located himself, when he begins to feel his way along the English Channel, he is guided by the coasting lights, and so long as they are of such range that he will never be out of sight of one or two of them, that will be sufficient. Thus, the Beachy Head light, in its present low position, has a sufficient range for its purpose, with the added advantage of more freedom from obscuration by fog. Thus, we see how the local conditions and the purpose of each particular light have to be taken into consideration in determining its position and power. The Eddystone, again, is an example of a further class. It simply serves to denote the position of a group of dangerous rocks. Its function is not so much guidance, although no doubt it often serves for that, but for warning. The lizard light beckons the oncoming ship to the safety of the English Channel. The Eddystone warns it away from danger. The latter, therefore, and similar lights are warning lights. Right at the entrance of the English Channel, that greatest of all highways for shipping, there lie the Skille Isles. This group comprises some few islands of fair size from which we draw those plentiful supplies of beautiful spring flowers. But it also includes a large number of rocky islets which have sent many a strong ship to its doom. On one of these islets, therefore, the Bishop's Rock, there now stands a very powerful light which exemplifies many whose purpose is the double one of welcoming the mariner as he approaches our shores and at the same time warning him of a local danger. Such are both making and warning lights. Of no less importance, though less impressive, are the guiding lights, which guide the ships into and out of harbors and through narrow channels. These are generally arranged in pairs, one of the pair being a little way behind and above the other. Thus, when the sailor sees them both, one exactly over the other, he knows he is on the right course. Sometimes lighthouses have subsidiary lights as well as the main light, to mark a passage between two dangers, or to give warning of some danger. The subsidiary lights are often colored, and they are generally sectors, showing not all around a complete circle, or even a considerable portion of one, but just in one certain direction. They are generally shown from a window in the tower lower down below the main light. Finally, it is important to remember that every light must be distinguishable from its neighbors. Hence, every one in any given locality has a different character from all the others. This character is given to it by means of flashes. Instead of showing, as the primitive lights did, a steady light, the modern lighthouse exhibits a series of flashes, the duration of which, together with the intervals between, give it its distinctive character. This flashing arrangement has a further advantage over the steady light. Each flash can be made more powerful than a steady light could be, but more of that later. The actual source of light varies with circumstances. The electric arc is, as we all know, a very powerful light. In fact, it can be made the most powerful of all, but its light is decidedly bluish. Now the time when a light is most of all needed is when the weather is thick. Fogs varying from a slight haze to a thick pall of darkness are very common occurrence, and the lighthouse must be able as far as possible to penetrate them. As a matter of fact, clean fog, such as one gets at sea, is not by any means opaque. The black fogs of the great cities are another matter, but they are not the sort which afflict the mariner. On a foggy day in the open country or by the sea it is often particularly light. Indeed, the light is of a peculiarly diffuse nature, which gives a nice even illumination to everything. Thus, we see the fog is really transparent, but it diffuses the light. It does not stop the light rays, but simply bends them about and scatters them in all directions. Thus, we can see nothing through the fog, yet a flood of light reaches us through it. In its effect, it is like that crinkled glass which is often used for partitions between rooms, which lets the light through, but which cannot be seen through. We see, then, that the effect which a fog produces is mainly to refract the light rays. Each little drop of water, for it must be remembered that fog is myriads of tiny drops of liquid, it is not vapor, acts like a minute lens, and bends the rays which pass through it. And the more blue a ray is, the more it is bent. On the contrary, the more red it is, the less is it bent. When a beam of light is analyzed in the spectroscope, the red rays are bent least and the blue rays most, so that the red rays fall at one end of the spectrum and the blue at the other. Now we only see a thing when light rays proceeding from every part of it fall straight, or nearly so, upon our eyes. Consequently, since red rays are bent and scattered by the fog less than the blue rays are, a red light will be more easily seen through a fog than a blue one. It might seem from this that a red glass put in front of a light would make it better for this purpose, but that is not the case, for the simple reason that filtering the light through red glass does not really make it any redder than it was before. It simply makes it look redder by extracting from the original light all except the red. But a source of light which is naturally reddish is so because it is more plentifully endowed with red rays, while a bluish light, like the electric arc, is naturally deficient in red rays. Consequently, we should be inclined to expect from theory that the electric arc would not be a good light for a lighthouse, since it would lack penetrating power in foggy weather. Some readers may have noticed themselves, in towns where electric lights and gas lamps are in use near each other, that the latter, though relatively feebler under normal conditions, seem to give more light in fog, and experiments show that this is really the case. So although there are some lighthouses with electric arc lights, that which is now believed to be the best is an oil lamp of special design, using a mantle of the Welsbach type. The oil is stored in strong steel reservoirs into which air is pumped by means of a pump not unlike those used to inflate bicycle tires. By this means, the pressure is maintained upon the oil of about 65 pounds per square inch. This forces the oil up a pipe and drives it in a jet into a vaporizer, a tube heated from the outside so that in it the oil is turned into gas. This gas then rises to the burner and heats the mantle, just as the gas does in the ordinary incandescent gas light. Indeed, in the case of lights on the mainland near a town, the gas from the town main is often utilized. But this simple arrangement for using vaporized oil, as will readily be seen, can be employed anywhere. A little of the gas produced is led through a branch pipe and burned to heat the vaporizer. To start the apparatus, the vaporizer is heated with a little methylated spirit. Thus everything is quite self-contained and so simple that there is little to get out of order. The largest size of lamp will give 2400 candle power, with an expenditure of 2 1/4 pints of oil per hour, just common oil too, of the kind used with ordinary wick lamps. Having got a source of powerful light, the next thing is to collect that light and throw it in the direction required. For the light proceeds from the lamp in all directions, practically, and much of it would be entirely wasted could it not be collected and guided in the required direction. The earliest attempt at this was to use a reflector of bright polished metal. In the most improved form, these were made to the peculiar curve known as a parabola. This is a curve obtained by cutting a cone in a certain way, wherefore it is one of the conic sections, and its particular appropriateness for this work resides in the fact that if a light be placed at a certain point known as the focus, all the diverging rays which fall upon the reflector will be reflected in the same direction, parallel to each other. An ordinary spherical mirror would reflect them either back to the lamp or in diverging directions. At any distance, the beam from the parabolic reflector will be more intense than that from the spherical one, since the rays will be closer together. But even with the parabolic one there is some diffusion, for the simple reason that whereas the focus is a mathematical point, position without magnitude, the most concentrated form of light known has a considerable magnitude. Hence, the rays proceeding from the center of the mantle are reflected as per the theory, but those from the outlying parts of it are somewhat diffused. This difficulty cannot possibly be overcome, and hence even in the finest examples of lighthouse architecture, the flashes are not quite sharp and clear-cut. There is a central moment, so to speak, wherein the flash is almost blinding in its intensity, but it is preceded by a period of growing brightness and succeeded by one of decreasing light. In the modern apparatus, however, metallic mirrors are entirely dispensed with, their place being taken by reflecting prisms of glass. The metallic ones had to be continually rubbed to keep them clean, and this soon dulled their brightness, while the glass prisms need only to be wiped carefully, which operation has little effect upon their surface. It may come as a surprise to some that reflecting prisms are possible. The idea of refraction through a prism is quite familiar. Such forms the essential principle of the spectroscope. Refraction is explained to every schoolchild in order to account for the rainbow, but reflection by a piece of the clearest glass seems a contradiction in terms, almost. Yet it is only a question of shape. In some prisms, the light is simply bent as it passes through. In others, it is bent twice, so that it leaves the prism just as if it had been reflected off a mirror. Both devices are used in the lighthouse. Let us see how they are combined so as to perform the work to be done. Take first of all the case of a light upon an isolated rock where the warning is needed equally all around. All that is necessary here is to pick up those rays which, if left to themselves, would fall upon the water near the foot of the tower, and those which would waste themselves skywards, and then to gather all the rays into several bundles or beams. We will suppose a simple case in which the light is supposed to give flashes at regular intervals. We are in the topmost room of the lighthouse, the lantern as it is called. In the center there stands the murette or pedestal. In this, several columns support a circular platform on the top of which there moves what we might call a turntable, which in turn bears a frame of gunmetal into which are fitted a maze of glass bars, triangular in section and curved to form concentric circles. The whole structure, possibly, is of great size. From the floor to the platform is as high as an ordinary man. Indeed, around the turntable there is a gallery which forms a roof over our heads, so that it is only after mounting some iron steps into this gallery that we are able to examine the glass part. As we ascend, we notice that the walls of the chamber as far up as the gallery are formed of iron plates, while above that there is a metal framework filled in with glass panes, and above all a dome-shaped roof. Having reached the platform, we proceed to examine the glass, and we find that the metal framework forms a cage with 4 sides, each approximately flat, but really slightly spherical. Each of these sides is called a panel. In the center of each is the lens. Peeping through the interstices between the prisms, we perceive that the lamp is inside the structure, exactly in the center, so that its light shines directly through the central lens or bull's-eye. Around this bull's-eye forming refracting prisms. Around this again are more bars in the form of segments, which together form circles, some being refracting prisms and others reflecting prisms. All the light rays from the lamp which fall on any one prism are deflected, so that they proceed approximately in the same direction. Those prisms in the upper part lay hold of the rays which would otherwise go up into the sky. Those at the bottom collect those which would fall near the foot of the tower, so scarcely any are lost. But for the fact that the lamp itself is comparatively large and not a theoretical point, as already explained, the beam from this panel would be perfectly straight, parallel, and of uniform density everywhere. As it is, it widens slightly as it proceeds, but, practically speaking, we might call it a solid beam of light. Each of the panels sends forth such a beam, so that they strike out in 4 directions from the central lamp, much as 4 spokes from the hub of a wheel. Then, descending once more to the floor from which we started, we see that among the columns there is a large clockwork arrangement, the purpose of which is to drive round the turntable and all that it carries. in the language of the lighthouse engineer, the optical apparatus, or more briefly, the apparatus. And as this turns, the radiating beams of light sweep out round the horizon and in succession strike into the eyes of any mariner who may be within range. Each time a beam strikes him, he sees a flash. If the apparatus revolves once a minute, he will see 4 flashes every minute, one from each panel. Let us consider, then, the advantages of this wonderful mechanism with its cunning arrangement of prisms. It is these latter, of course, which are the important thing. The rest, the mechanical portion, is simply for the purpose of holding them and turning them at the proper speed. In the first place, the contrivance gives us flashes instead of a steady light. It gives the lighthouse its character. Then again, it enhances the brightness of the light. Instead of shining all around, the light is concentrated in 4 special directions, and the light which would be wasted upwards or downwards is saved and brought into use. But suppose that the lighthouse we are considering be near the shore, so that there is no need for it to throw any light in the landward direction. Then we should see inside the revolving framework with its prisms a fixed frame with reflecting prisms which would catch any rays going from the lamp in the direction of the land and simply hurl them, as it were, back into the flame. Thus, the intensity of flame becomes increased by those rays thrown back which would else have been wasted. Or suppose that the character of the light is such that the flashes have to be at irregular intervals. Then the framework, instead of being symmetrically 4-sided, would be of an irregular shape. And that brings us to a beautiful feature of the mechanism of the apparatus. We have been discussing a 4-panel arrangement. Suppose that we were to reduce it to 3, then since all the light would be concentrated into 3 beams instead of 4, each beam would be more intense. We should thereby have the increased range of our apparatus without any increase in the cost of oil, for nothing, as it were. But to get the same number of flashes per minute, we should have to drive it round so much faster. But increased speed means increased burden on the keepers who have to wind up the heavy weights which operate the clockwork. So there is a limit to the speed which can be attained. But if friction can be almost eliminated, the apparatus can revolve at a high speed without throwing undue burden upon the men. But how can friction thus be got rid of? Messrs. Chance Brothers, the great lighthouse constructors of Birmingham, have done it, almost entirely, by floating the apparatus on mercury. The turntable has on its underside a large ring which nearly fits a cast-iron trough on the top of the pedestal. In this trough there is mercury, so that upon the liquid metal the apparatus floats as if upon a circular raft. The table with its lenses, prisms, and other fittings may weigh 6 or 7 tons, yet it can be pushed around by one finger. The various sizes of optical apparatus are known as orders. One of the first order has a focal distance of 920 millimeters. This means that there is that distance between the center of the lamp and the bullseye. They descend by successive stages down to the 6th order, with a focal distance of 150 millimeters, while the most important lights are of an order superior even to the so-called first, termed the hyperradial, the focal distance of which is 1,330 millimeters. A recent example of a hyperradial light is at the well-known Cape Race in Newfoundland. It revolves once every 30 seconds, giving a flash of 3 seconds every 7.5 seconds. The optical apparatus weighs 7 tons. Most lighthouses are fitted with fog signals of some kind, which have a distinctive character the same as the lights. Some are horns blown at intervals by compressed air, often obtained from a special air pump driven by an oil engine. Another thing is to let off detonators at stated intervals. But perhaps the most interesting of all is the submarine telephone. The trouble with audible signals is that they are apt to vary as the conditions of the atmosphere change. For, strange though it may appear, the air which is the natural medium by which sounds are carried to our ears is really a very bad substance for the purpose. Water is much superior. A swimmer who cares to try the experiment of lying upon the water with his ears immersed, while a friend beats a gong under the water some distance off, will be astounded at the result. So many modern ships are fitted with underwater ears, waterproof telephone receivers really. One is fixed each side of the vessel, the wires from them being led to the telephone receivers near the bridge. Many lighthouses and lightships in like manner are fitted with underwater bells which can be rung at intervals. The sounds so conveyed through the water are always the same. Atmospheric or similar changes have no effect upon them, and, moreover, the officer can tell which side of his ship the bell is. If it be on his port side, it sounds louder in his port telephone, and vice versa. By turning his ship until he hears them equally, he knows that he is pointing directly to or from the bell. Thus, if the bell belong to a warning light, he can steer confidently right away from the danger even in the thickest fog. But science has not only provided the mariner with lights of marvelous power and of strange distinctive characters, and reliable sound signals for foggy weather, it has also found him a reliable compass, but that is worthy of a chapter to itself. End of section 6. Recording by Arvind Sundar from arvindsundar.com.
Section 7 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. The Gyro Compass. The magnetic compass has been for ages the mariner's guide over the trackless waters. In cloudy weather, it has been his only means of knowing the direction in which his craft was heading. Indeed, it is not too much to say that the maritime compass of the world was based upon the behavior of that little piece of magnetized steel. It has always, however, been subject to certain faults. To commence with, it points not to the geographical north, but to the magnetic pole. It points some distance from the geographical pole, and one moreover which is not quite permanent. The fact that the magnetic pole varies its position is impressively shown by the fact that a special department at the Greenwich Observatory is continually employed by the aid of delicate self-recording instruments, watching and setting down its fluctuations. And the premier observatory of the world, it should be remembered, exists primarily not in the interests of pure science, but as the department of the British Admiralty in order to study matters of interest to navigation. Thus we have testimony to the importance of these little vagaries on the part of the magnetic compass. But in addition to these inherent faults, there is a new source of error in the magnetic compass which man has introduced himself by making his ships of iron instead of wood. Every ship of the present day is a huge magnet. A piece of iron left in the same position for a length of time becomes polarized, which is to say that it acquires the properties of a magnet, and two magnets always exert an influence upon each other. Consequently, the ship, after lying for perhaps a year in one position during the period of building, becomes itself magnetic and interferes with its own compass. Then again, our methods of ship construction aggravate this trouble. It is believed that every molecule of iron is itself a minute magnet with the north and south pole of its own. These, lying in confusion in the mass of unmagnetized iron, neutralize each other, so that the mass taken as a whole does not exhibit any magnetic power. But if by some means the whole of the millions of molecules can be set the same way, with all their north poles in one direction and their south poles in the opposite direction, then they will all act together. Instead of neutralizing each other, they will then help each other, and under those conditions, the mass of iron will possess that peculiar power which is distinctive of a magnet. So long as a piece of iron is left in the same position, the magnetism of the earth is thus acting upon the molecules. Just as it tends to place the compass needle north and south, so it does with every molecule in the iron mass. And if, while lying still, the iron be hammered, the shaking of the molecules due to the hammering loosens them, as it were, and assists the earth's power in pulling them into position. One has only then to watch the riveting up of a ship, and to see the vigorous way in which the riveters wield their hammers, to realize when the thousands or even millions of rivets have all been finished, the material of that ship will have had the very best possible chance of becoming magnetic. To make matters worse still, ships are often loaded with great weights of iron among their cargo. That too may affect the compass. On warships there are the heavy guns, each weighing with its turret hundreds of tons, and they move, so that their effect upon the compass is not always the same, but may vary from time to time. And finally, one may mention the electrical machinery in a modern ship consisting largely of powerful magnets. Altogether then it is not surprising that the old magnetic compass is somewhat unreliable. It has to be coaxed into doing its duty. Pieces of iron and magnets have to be disposed about it to counteract these disturbing influences with which it is surrounded. Before a voyage, experts have to come on board to adjust the compasses, and even then there is reason to believe that the instrument sometimes plays the ship false. It is not to be wondered at then that the naval authorities in particular throughout the world have welcomed the advent of a new compass, which appears to possess none of these drawbacks. It points to the geographical north, to the actual pivot, if one may so speak, upon which the Earth turns. It is non-magnetic, so that the presence of iron or magnets even in its immediate neighbourhood has little or no effect upon it. On the other hand, it has to be driven by a current of electricity, and it seems just possible that in some great crisis it might fail. Although every provision is made for alternative sources of supply in case of one failing, and there is always the possibility of falling back upon the old magnetic compass should the new one go wrong. In principle, the improved compass is like its older brother, simplicity itself. The latter is but a small piece of iron magnetized. The former is nothing more than a spinning top. It is rather strange that although the spinning object has been a familiar toy for years, and that moreover its behavior has been the subject of investigation by some very eminent scientific men, it is only of recent years that its principles have been put to practical use. Everyone is familiar with the fact that a round block of wood will support itself upon a comparatively tall peg so long as it is rapidly rotating. And that is but one of the curious things which a rotating body will do. For example, imagine a wheel mounted upon an axle, the ends of which are supported inside a ring, while the ring again is supported on pivots between the two prongs of a fork, the fork being free to swivel round in a socket. The wheel is then free to move in any direction. Technically, it is said to have 3 degrees of freedom. It can spin round, its axle can turn over and over, with the pivoted ring inside which it is fixed, while it can also swing round and round as the fork turns in its socket. Assuming that the joints are all perfectly free, that the pivots move in their sockets with perfect freedom, which of course they do not, then a wheel so mounted could move in any direction under the influence of any force that might act upon it. Now, a wheel so mounted, if left alone, remains in precisely the same position so long as it goes on rotating. If it be turning sufficiently quickly, its tendency to remain will be strong enough to overcome the friction of any ordinarily well-made instrument. Consequently, a wheel of that description has been used to demonstrate the rotation of the Earth, it remaining still, except of course for its rotating movement, while the Earth has moved under it. Could we entirely eliminate the effects of friction that might be used as a compass, for it could be set, say with its axle pointing north and south, at the commencement of the voyage, and it would remain so despite all the evolutions through which the ship might go. But there is a better scheme even than that, based upon the peculiar behavior of a revolving wheel when it has only 2 degrees of freedom. Suppose that we dispense with the ring, employed in the previous arrangement, pivoting the ends of the axle between the prongs of the fork. The wheel is then free to rotate, and its axle can slew round through a complete circle by the turning of the fork in its socket, but there can be no tilting of the axle. Being thus deprived of one of its movements, the gyroscope with 3 degrees becomes a gyroscope with 2 degrees of freedom, and in that form it supplies the need for an efficient and reliable compass. The secret of the whole thing is the curious fact that a gyroscope with 2 degrees of freedom exhibits a keen desire to place its axis parallel with the axis of the Earth. Owing to the shape of the Earth, a device such as has been described, with its fork standing up vertically, cannot possibly have its axis really parallel with that of the Earth, except on the equator. Still, it gets as nearly parallel as possible. To be scientifically accurate, we ought to say that it places its own axis in the same plane as that of the Earth. To understand this, we need to realize that all movement is relative. In ordinary language, when we say a thing is still, we mean that it is still in relation to the surface of the Earth. But since the Earth is moving, the stillest thing, apparently, is really travelling at enormous speed. St. Paul's Cathedral in London, or a tall skyscraper in New York, would usually be regarded as supreme instances of immobility. It would be hard to find better examples of stationariness as we ordinarily look at things. Each stands firm and strong upon a horizontal base, yet each is really turning a somersault every 24 hours. The plateau upon which St. Paul's stands, though it seems still and motionless beneath our feet, is continually tilting. Its eastern edge is continually going downwards, and its western edge upwards as the earth performs its daily spin. It is only a north and south line which does not share in some degree this continual tilting action. Every plane, large or small, so long as it remains horizontal, is being tilted thus, down at the eastern edge and up at the western. And the plane in which the axle of a gyroscope with 2 degrees is free to move is a horizontal plane. Owing to its being held between the prongs of the fork, while it can swing round to point north, south, east or west, or towards any point between them, it cannot deviate from the horizontal plane. Therefore, such axle is always being tilted by the motion of the earth, except when it happens to be lying exactly north and south. Now, for a reason which is too complex to go into here, a gyroscope strongly objects to having its axle tilted in this manner. If it be compelled by superior force to submit to tilting, it tries to wrench itself round sideways. Anyone who has a gyroscope top and cares to try the experiment will feel this action quite easily. Hold the spinning top in your hand and turn it over so as to tilt the axle, when it will, if you are not careful, twist itself out of your grasp. So a gyroscope of the kind we are considering, when the motion of the earth tilts its axis, turns itself round in its socket until at last it reaches the north and south position, when the tilting and therefore the twisting ceases. Hence the axle of the gyroscope, if left to itself, the rotation of the wheel being maintained the while, will place itself in a north and south direction, and moreover it will keep in that direction. It will take some force to slew it round into any other, and if moved into any other by some extraneous means, it will restore itself to the old position again. Hence a wheel thus arranged has all the attributes which we need for a mariner's compass. But unfortunately, there are mechanical difficulties in the way of using such a simple contrivance for that purpose. Chief of all these is the fact that it is not what engineers call dead beat. That means that it will not go to the proper position and then remain there quite still. Instead, it will first slightly overshoot the mark, which being followed by the reverse action, it will come back and overshoot it just as far in the opposite direction. Instead, therefore, of a steady pointing, always in the same direction precisely, it will oscillate more or less, the exact north and south line being the mean or average position, the center of the oscillations. It would of course be possible to damp this, to apply a brake as it were, if the apparatus were to remain stationary. For example, if the whole concern were immersed in water, the resistance of the liquid would restrain any quick movement of the axle, yet it would not prevent it from slowly finding its true position. Thus, the oscillations would be reduced to such a small range as to be, for practical purposes, negligible. But the drawback to a device of that kind, applied to a gyroscope on board ship, would be that the axle would be carried round to some extent every time the ship turned. As she changed direction, it would more or less carry round the water with it. That in turn would carry the gyroscope, and so the direction of the latter would be for a time untrue. It would in course of time regain its accuracy, but in the meantime it would be leading the ship astray. Consequently, the application of this in itself wonderfully simple idea to this extremely important purpose was accompanied with a difficulty which was for a long time insuperable. But all was overcome at last by the genius of Dr. Anschutz of Hamburg, whose firm were the first to turn out the practicable article. Taking advantage of another movement of the gyroscope, when arranged as has been described, and using the revolving wheel itself as a centrifugal fan, he was able to make the wheel blow air against itself, as it were, when in any position other than north and south. Thus, if it deviates towards the east, this jet of air tends to blow it back. If it turns westwards, the jet again comes into operation, tending to bring the airing gyro back to its proper place, and so the tendency to oscillate is checked. The finished instrument, as it is installed on the latest warships, is of course quite different in detail from the simple contrivance which we have been considering so far, although it is the same precisely in principle. The essential part is a heavy metal wheel, combined with which is an electric motor, which keeps it rotating at a speed of 20,000 or so times per minute. The bearings of the wheel are supported upon a metal ring, which floats upon the surface of a trough of mercury. Thus, friction is brought down almost to the irreducible minimum. The only place where the wheel and its support touch anything solid is at one delicately made pivot, which serves to keep the floating mechanism in the center of the mercury basin, and to prevent it from rubbing against the side of it. The current which drives the motor reaches it through this pivot and leaves through the mercury. Thus arranged, although the floating part is of considerable weight, a very slight force indeed is enough to move it. While looking at it the other way, we can see that the ship might turn rapidly to right or to left, carrying round the mercury bowl with it, without turning the floating part at all. Thus, the gyroscopic action is very free indeed to exercise its function of keeping the contrivance pointing always in the one way. The float has mounted upon it a compass card, much like that of the ordinary magnetic instrument, and the sailor reads it in precisely the same way. To outward appearance, there is little essential difference. In one case, there is a magnet under the card to keep it still, in the other, there is the float with the revolving wheel mounted upon it. It is customary to have one master compass of this kind on a ship with an electrical repeater in each of the steering positions. As the master turns in its casing, it sends a rapid series of currents to all the others, causing them to turn in unison with it. The master is fitted in some safe part of the ship where it is least likely to be the victim of any accidental damage. End of section 7.
Chapter 8 of Marvels of Scientific Invention by Thomas W. Corbin. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gary Leo Smith. Marvels of Scientific Invention by Thomas W. Corbin. Chapter 8, Torpedoes and Submarine Mines. It is sad to think how much scientific skill and learning has, during the Great War, been devoted to killing people. It used to be thought that one day a great scientific invention would arise, of such deadly power that forever afterwards war would be unthinkable. Its horrors would be such that all nations would shrink from it. That prophecy, however, has not been fulfilled, nor are there any signs of it. On the contrary, each scientific achievement in the realm of warfare is quickly countered by another, so much so that with all our science in the manufacture of weapons and our skill in using them, warfare in the 20th century is, if anything, less deadly in proportion to the numbers engaged than it used to be. There are, however, two weapons which in this war have reached a deadly efficiency, which they did not seem to possess before, and to which satisfactory antidotes have not yet appeared. These two are the submarine mine and the torpedo. The latter particularly had been a dismal failure previously, but as the weapon of the submarine it has now established itself. It is, however, only in connection with the submarine that it has achieved any measure of success, and as there are strong indications that very soon the submarine itself will be robbed of its terrors, it is quite likely that the reign of the torpedo will be brief. Although it has only just made itself felt seriously in warfare, the torpedo is a fairly old idea. In fact, we can trace the general idea of it back to very ancient times. The modern weapon, however, dates from the year 1864, when an Austrian inventor approached an English engineer named Whitehead with a request to take up his idea. Mr. Whitehead had at the time a works at Ufume on the Adriatic, and it was really his genius that developed the crude idea into a practicable invention. Thus there came into existence the Whitehead torpedo, now used in a great many navies, and also the Schwarzkopf, which may be regarded as the German variety of the same thing. Speaking generally, it may be described as a small automatic submarine boat. Externally, it naturally follows somewhat the lines of a fish, deriving its name from that curious fish which is able to give electric shocks from its snout. It likewise carries on its nose that appliance whereby it gives a shock, not electric, it's true, but equally deadly to anything which it may touch. Since no man-made mechanism can approach the marvelous action of a fish's fins and tail, the propulsion is achieved by a propeller like that of a steamboat, but of course on a very small scale. A single propeller, however, would tend to turn the torpedo over and over in the water, and so it has two, one behind the other, driven in opposite ways, so that the turning tendency of one is neutralized by that of the other. The blades of the propeller are, however, set in opposite ways, so that although rotating in different directions, they both push the torpedo along. Behind the propellers, again, there are rudders for steering. One steers to the right or left, as does that of an ordinary ship, while two others are so placed that they can steer upwards or downwards. So there we have the general picture of the outside, a smooth, fish-like body with a sting in its nose, propellers at the rear to drive it along, and rudders to guide it. Inside are various chambers. One contains the explosive which blows up when the nose strikes something. This head, as it is termed, is detachable, so that it can be left off until it is really required for war. The peace head, which is of the same size, shape, and weight as the warhead, is what the torpedo carries during its earlier career. With this, it can be tried and tested in safety, the warhead being substituted when the real business of the torpedo begins. Another chamber contains the compressed air which furnishes the motive power. This also serves to give buoyancy. Another chamber again contains the engines, beautiful little things of the finest workmanship, almost exactly like the finest steam engine, but of course very small in comparison. In the early stages, the range of the torpedo was limited by the amount of compressed air which it could carry. At first sight, there seems no reason why any limit should be placed upon this, but in practice there are often limitations in engineering matters which are not apparent on the surface. For example, to increase the air chamber would mean enlarging the whole torpedo, calling for more propulsive power and larger engines, and these larger engines would call for more air, thus defeating the object in view. Forcing more air in by using a higher pressure in a similar way would necessitate a thicker chamber to resist the higher pressure. This would add weight, calling for more buoyancy. Thus there seemed to be a practical limit beyond which it was impossible to go. The difficulty was overcome, however, in a very cunning way. When the engines have used some of the air and the store is somewhat exhausted, chemicals come into action which generate heat, which is imparted to the air which is left. This heat expands the air, producing in effect a larger supply of it, and enabling the torpedo to make a longer journey. Steering in a horizontal direction, that is to say, to left or right, is done by a gyroscope. The action of a rotating wheel is discussed in the last chapter, and it is not necessary here to say more than this. A rotating wheel always tries to keep its axle pointed in the same direction. Just at the moment of starting such a wheel is set going inside a torpedo, its arrangement is such that, should the torpedo swerve to the left, the gyroscope operates the rudder and steers it back. In the same way, if it tends to turn to the right, the ever-watchful gyroscope brings it to its true course once more. The effect of the gyroscope, therefore, acting upon the rudder, is to keep the torpedo faithfully to the direction upon which it is started. The up and down rudders are likewise controlled quite automatically, but in a different way. Their function clearly is to keep the thing at a certain uniform level. Without such control, a torpedo would be equally likely to jump out of the water altogether, or to go downwards vertically and bury its nose in the mud. The depth at which it is to move is determined beforehand. Certain necessary adjustments are made, and the torpedo then pursues its even way, neither coming to the surface nor driving beneath its target. For this purpose there is first of all a hydrostatic valve. This little appliance, which is open to the action of the water, responds to changes in pressure. The pressure at any point under water is exactly proportional to the depth. At 10 feet, for example, it is precisely 10 times what it is at 1 foot. So the hydrostatic valve is adjusted to set the rudder straight when the water pressure upon it is a certain amount. If then it dives downwards, the pressure increases and the valve operates the rudders so as to bring it upwards, while if it rise too high, the decrease of pressure causes it to be guided downwards. This action, however, is too sudden and violent, so that with it alone the torpedo would proceed by leaps and bounds. After being low, it would come up too suddenly, overshoot the mark, only to be steered downwards again equally suddenly. The valve, therefore, is combined with a pendulum, whose actions tends to restrain these too sudden changes, with the result that under the influence of the two things combined, the torpedo keeps fairly well to an even course, only varying upwards or downwards to an extent which is negligible. Finally, there is an interesting little feature about the firing mechanism which merits a description. The actual firing is caused by the driving in of a little pin which projects at the nose of the torpedo. Suppose that in the process of pointing the torpedo and launching it upon its course, that pin were to be knocked accidentally. An awful disaster would result. It must be provided against, therefore, and the method adopted is beautiful in its certainty and simplicity. Normally, the firing pin is fixed by a screw so securely that no accidental firing is possible. There is, however, a little propeller-like object associated with it, which is driven round by the water as the torpedo is pushed through it, and this unscrews and thereby releases the pin. The little fan has to rotate a certain number of times before the pin is released, and it is quite impossible for this number to be accomplished before the torpedo has proceeded to a safe distance from the ship which fires it. On board the ship, therefore, and so long as it is near the ship, it is quite safe, but by the time it reaches its target, it is ready to explode. As far as is known, the foregoing description gives a true general description of the torpedoes now in use. Those of different powers may vary in detail, but broadly they are as just described. There are others, however. The Brennan, for instance, was once adopted and largely used by the British for harbor defense. This was controlled from the shore by wires. It was driven, so to speak, with wire reins, and thus guided it could fairly hunt down its prey, turning to right and to left as required. Of greater scientific interest, perhaps, still, is the Armour 1 wireless-controlled torpedo. This is the invention of two gentlemen, Messrs. Armstrong and Orling, whose first syllables combine to form the title of the torpedo. Of this, two very interesting features may be mentioned. Firstly, the wireless control. In the chapter on wireless telegraphy, there is described the coherer, a simple little apparatus which we might describe as a door which is opened by the waves which travel through the ether from the sending apparatus. Whenever the key of the sending apparatus is depressed, these waves travel forth, and when they fall upon the coherer, it opens. Normally the coherer is shut, but when acted upon by the incoming waves, it opens and lets through the current from a battery, which current can be caused to perform any duty which we may wish. Thus, ignoring the intermediate steps, we get this. Whenever the sending key is depressed, current flows through the coherer and performs whatever duty is set before it. And now picture to yourself a tooth wheel with 4 teeth. A catch normally holds one of the teeth, but when the catch is lifted for a moment, it lets that tooth slip and the next one is caught. At every lifting of the catch, the wheel turns a quarter of a turn. Then imagine that catch is operated by an electromagnet energized by the current which passes through the coherer. We see then that every time the sending key is depressed, the wheel turns a quarter turn. Attached to the wheel is a little crank which turns with it, and the pin of this crank fits in a slot in the end of a bar like the tiller of a boat. Suppose that, to commence with, the tiller is straight, so as to steer the boat straight. Depress the key, the wheel turns a quarter turn, and the tiller is set so as to steer to one side, say the left. Another pressure upon the key and a second quarter turn brings the tiller straight again. Yet another pressure, another quarter turn, and the tiller is steering to the right. Thus, by simply depressing the key the correct number of times, the torpedo can be made to travel in any desired direction. The second ingenious feature of this weapon is the means by which it is made visible to the man who is controlling it from the shore or ship. Probably the reason why these torpedoes are not used more is that the man who guides them is of necessity himself visible. He has to be posted somewhere where he can follow its course, or he has no idea how to steer it. Consequently, he would be an object for attack by the enemy. Such a torpedo would be useless in a submarine, for the submarine would need to come to the surface in order that the observer might get a sufficiently good view to be able to steer the torpedo, and we all know that when upon the surface a submarine is a very vulnerable craft. But that is by the way. The point is how to make the torpedo very clearly visible while it is still underwater. A short mast might be used, but that would be liable to be shot away. The inventor had a happy inspiration when he made it blow up a jet of water like a whale does. This jet is quite easy to see, yet no shot can destroy it. Compressed air blows up this telltale jet which the observer can see, and by its means he can guide the torpedo at will. A submarine mine may be regarded as a stationary torpedo. It consists of a metal case filled with a powerful charge of explosive which floats harmlessly in the water until some unfortunate vessel strikes against it, when it blows up with sufficient force to make a hole in the stoutest ship. There are two classes of mine, one which is laid in peacetime to protect harbors and channels, and the other which is laid during actual warfare. The former are anchored in a more or less permanent way. The services of divers are used to place them in position. In some cases, they float well down in the water, out of the way of passing ships, but come up nearer the surface when needed. This result is achieved by having an anchor chain of such length that when fully extended the mine floats a little way under the surface, just high enough to be struck by a passing ship, together with what is called an explosive link. The link is used to loop together two parts of the chain, and so in effect to reduce its length. Wires pass from the link to the shore, and when an electric current is sent along these wires, the link bursts asunder, liberates the chain, and the mine floats up to the full length of its chain. Another plan is to let the mines float high up always, but to fire them not by the touch of the ship, but by electricity from the shore. In this way a safe channel is kept for friendly vessels, while an enemy can be destroyed. Necessarily, those mines which are hurriedly laid in wartime are very different from these. To be of much use, a mine must be concealed below the surface. If it floats upon the water, it will be visible, and can be avoided, or, at all events, easily picked up. It is practically impossible to set a floating object at a certain depth in the water, except by anchoring it to another, heavier object, which will lie at the bottom. Therefore mines have to be anchored in some way. But the sea varies in depth, so that the length of the anchor chain must be varied, or else some of the mines will be on the surface, thereby advertising the presence of a minefield, while others will be below the depth of even the biggest ship. In warfare, however, mines need to be laid quickly. There is no time to sound for the depth and then to adjust the length of the cable accordingly. Hence the mine must be so made as to set itself correctly at a predetermined depth. Possibly some readers may think that such things might be made to float of themselves at the right depth. It is a fact, however, that a thing either floats upon the surface of the water or falls to the bottom. Water is practically incompressible, so that the water at the bottom of the sea is no heavier than that near the surface. The conditions which prevail in air and allow a balloon to float at any desired height do not apply. The only thing in this case is to have an anchor chain or rope of the right length. So let us picture a mine-laying ship steaming along, probably in the dead of night, surreptitiously laying mines in the hope that the enemy will run into them on the morrow. Along the deck of the ship are small railway lines, and on these lines stand what appear to be trains of small trucks, each truck having small wheels to run on, and each bearing a large round metal ball. As the ship travels along, the crew, handling these deadly things quite freely, as if they were innocent of any danger, propel them along to the stern, and at regular intervals push one overboard. That is all. The freedom with which the men handle them is not folly, for they are then quite harmless, nor need they trouble about the length of rope, for that adjusts itself. Just tumble the things overboard, and in due time they anchor themselves at the right depth and set themselves to the right condition for blowing up any ship which may get amongst them. The truck-like object upon wheels is not the mine itself. It is the sinker which lies at the bottom of the sea. The round ball which it bears is the mine, and the two are connected together by a wire rope. To commence with, this rope is coiled upon a drum in the sinker, which drum is either held tightly or is free to revolve according to the position of the catch. That catch is held open so that the drum is free by a weight at the end of a short rope. Let us assume that that rope is 10 feet long. Then, when the whole thing is tumbled into the water, the weight sinks first 10 feet below the sinker, which, being more bulky in proportion to its weight, follows downward more slowly. While sinking, the weight is pulled upon its rope and holding open that catch, so that the drum pays out its rope and the mine lies serenely upon the surface. As soon as the weight touches bottom, however, the pull on the short rope ceases. The catch grips the drum, no more rope is paid out, and the sinker, in settling down its last 10 feet, has to drag the mine down too. Thus, quite automatically, by what is really a beautifully simple arrangement, the mine becomes automatically anchored at a depth below the surface equal to the length of the short rope. By making that rope the desired length, the depth of the mine under the water can be fixed. There are various methods of firing these mines, all of which work perforce by the concussion of the ship itself. In some cases, the sudden tilting over causes an electric contact to be made and permits a battery in the mine to cause the explosion. Another way is to furnish the mine with projecting horns of soft metal, inside which are glass vessels containing chemicals. The ship, striking a horn, bends it, breaks the glass, and liberates the chemicals which cause the explosion. In the type of mine largely used by the British Navy, there is a projecting arm pivoted on the top of the mine and projecting from it horizontally. The mine itself rolls along the side of the passing ship, but the arm simply trails and scrapes along. Thus the mine turns in relation to the arm, and a trigger is thereby released which fires the mine. In this, to be noted, the ship only pulls the trigger, so to speak, and releases a hammer which does the work, just as the trigger of a gun releases the hammer. The motive force, which makes the hammer do its work when the trigger is pulled, is the pull on the anchor rope. That arrangement has a virtue which is not apparent at first sight. Since it is the pull on the anchor rope which actually fires the mine, it follows that if such a mine break away from its moorings, it instantly becomes harmless. Safety for the men who lay the mines is secured in several ways. One is by the use of a hydrostatic valve. The firing mechanism is locked until the pressure of water releases it, and that pressure does not exist until the mine is several feet under water. Another way is to seal up the firing mechanism with a soluble seal made of some substance such as sal ammoniac. The mine cannot then explode until it has been under water long enough for the seal to be melted. It now remains to relate how these mines are swept up and removed, yet there is very little really to tell, for the process is so exceedingly simple. So far as is generally known, no method has been found that is superior to the primitive plan of dragging a rope along between two ships so as to catch the anchor ropes. The vessels employed are usually of very light draft, so that they stand a good chance of passing over the mines themselves, and the rope used is as long as possible, so that a mine, if exploded by being caught in the loop of the rope, explodes so far away as to do no harm. When dragged to the surface, the mines are exploded from a distance by shots from a small gun, or even from a rifle. In the case of those mines which have horns, a blow from a bullet is enough to break the glass and cause explosion, and in all cases, mines seem sooner or later to succumb to a sharp blow. Thus they are destroyed by their own action at a safe distance from the sweepers. Accidents happen, however, and mine sweeping is no job for anyone but the bravest. It has been somewhat difficult to crowd a description of torpedoes and mines into the small space of one chapter, and so many details have had to be omitted. But the above descriptions give the broad general principles underlying practically all forms of these terrible weapons. This is the end of Chapter 8, recorded by Gary Leo Smith, Dublin, Ohio.